All right. Hi, everyone. So the broadcast should be started now. This is, I believe, the third CS video. I've been away for a while. I've been having some technical issues with Discord, with mics, etc. A lot of stuff. Work has been crazy. So finally found some time to get back to what I love, which is mathematics. Okay. So what we want to do today is continue where we started. We've started studying algorithms, which will prepare us, hopefully, turn us into better developers, and then prepare us for interviews and all this good stuff. Plus, it's math, so it's all great. Now we've gotten here to 2.3. This is where we're going to start today. Um, I am gonna share my screen so you guys can see me. Here we go. So here we are. This is CLRS section 2.3. Designing algorithms. So this is quite a hefty topic, right? How do you design algorithms? And honestly, I've been applying math in the field of artificial intelligence for a while, designing algorithms. Not for a while, but for about a year. And one thing I've learned is that designing algorithms hardly is ever is hardly ever a cookbook process. You have to think, and it's really it's domain dependent. The design of the algorithm is very domain dependent. However, there are certain approaches that at least basic algorithms have in common. There are a few approaches. They're fundamental techniques. And so one of them is an incremental approach. So right here we see a highlighted incremental approach. What is an incremental approach? Incremental approach is something like insertion sort, which we saw last time, where what we have is the following. We have an array of some numbers. Here's a list of some numbers, 1, -1, 3, and for simplicity, let's just say they do not repeat, -2, 7, 6. Our goal is to sort them. And insertion sort, the reason it's incremental is because insertion sort has an invariant where it's an iterative process. We go through a loop, and each time through a loop, we draw a bar. And we say that everything to the left of this bar is sorted. Our job is to sort everything to the right of the bar. Second time through the loop, we'll say the bar will move over one, like so. And we'll say again, everything to the left of the bar is now sorted. This is step 1, this is step 2, and then we go to step 3. And this time we say again, the bar moves over to the right and everything to the left of the bar is sorted. And our job is to sort everything to the right of the bar. So you see this incremental approach where each step through our loop, we guarantee that everything to the left of this bar is going to be sorted. These are incremental algorithms. Incremental. So that's what the book mentions here. Now, there is a second approach, general approach to algorithms, which is called divide and conquer. Now, what is divide and conquer? Divide and conquer is when we have this large problem. We have a large problem. So we have a box, and this is our problem. We need to solve this problem. Now, this problem is large, and maybe we don't quite understand how to solve it because it's quite complex. But what we do know is if I could break down this problem, somehow cut it into two pieces, where I have a problem here and a problem here, then maybe I could solve these two smaller problems. And then if I attached those two solutions, I would have a solution to the larger problem. Now, this is not always the case because you might say, okay, I may be able to solve this left sub-problem and this right sub-problem, but maybe I cannot attach them easily. I can just put them together. Let me show you an example so this abstract idea becomes a little more concrete. Suppose our goal is the following. So our goal is to take, again, a list of numbers -2, let's say -7, 8, and sort them. Now you might say, all right, so this is a pretty, this is a list of numbers. It has six numbers in it. I do not know how to sort uh, a list with 6 things in it. It's too large. Let me cut it in half. So we cut this in half. Now we have a list over here, -1, 3, and 4. And another list over here, -2, -7, and 8. Now we have the same problem. Our problem is sorting, right? We still need to sort these two lists, but now each individual list is smaller than the original one. So our two sub-problems are smaller in nature. Okay? And in a lot of situations, this ends up simplifying the problem. Just the size of the problem being smaller ends up simplifying the problem itself. So now, suppose we can solve this. Suppose we know how to sort lists of size 3. And we go ahead and do that. So we sort them. -1, 3, and 4. This one's sorted. There's nothing to do. This one we sort -7, -2, and 8. And now we need to do this step, this combination, the reattachment of these two subproblems into the solution of this larger one. Well, now you say, can I just put them together? No, I can't, because clearly -7 is not smaller than 4. I mean, it's not larger, of course, it's smaller. It's not larger than 4. So I cannot just concatenate these two lists. There's another thing I need to do. I have to merge them, somehow putting everything in their right place. But this merging procedure is not difficult if you think about it. Why is it not difficult? Because the respective lists, the left and the right one, they're already sorted. So what can I do? I can do the following. I can now say, let's keep track of, starting from the leftmost position, let's keep track of each element in these two lists. Let's compare these first ones. -7, -1. Which one's smaller? -7. Toss it in a new list. Okay, we put this -7 here already. Move this arrow over to the right. Which one's smaller, -2 or -1? -2. Toss it in the list. Move the arrow over. Which one is smaller, 8 or -1? -1. Put it here. Move the arrow over. Which one is smaller, 3 or 8? 3. Put it here. Move the arrow over. Which one is smaller, 4 or 8? 4. And finally, 8. And we're done. So the merging two sorted arrays is simple. Every time, it's simple in a sense that every time I'm looking at one of the elements in an array, and I'm going to look at it at most once. See, I looked at -7, I put it here, I crossed it out. I never have to look at -7 again. Then what happened? We compared -2 and -1. I looked at -2, I put it here, I crossed it out. I never have to look at it again. So we go through the elements in both arrays at most once. In fact, yeah, so we go as we put them in the bucket at most once. Another way to say it, at each step, one of the elements from either of these two arrays gets tossed out at each step. And so since we had 6 elements in total, we did 6 steps. So if you had n elements in total in these two arrays together, then we did approximately n steps to merge them. Okay? So this is the idea of divide and conquer. In general, I gave you a specific example. The example was sort this array, but the idea is you have some large problem. We split it up into smaller portions. If these portions are large in themselves, we cannot solve them, or we don't know how to solve them easily, split those respectively as well until you get to some atomic smallest value that you do, smallest problem that you do know how to solve those, and then recombine these sub solutions. Now, how do you recombine them? That's another question. So in this case, recombination was merging. We knew how to solve the problem of lists of size 3. We knew how to sort them, and the recombination constituted merging the two together, and we're done. So this is the essence of divide and conquer. Now, many useful algorithms are recursive. So what does it mean for an algorithm to be recursive? An algorithm is recursive if, when solving the sub problem, the algorithm essentially does the same routine. Okay, so the problem starts. The problem says, here's our goal: solve this, sort this list. Well, to sort this list, what did we do? We said sort this list and this list. So in order to sort, our job is to sort. This is what we need to do. We don't know how to sort. We're trying to implement this. In order to sort the large list, we called the same function on the smaller lists. Smaller lists. This is called a recursive process, where a procedure calls itself to solve smaller subproblems and then recombines the solutions of the smaller subproblems to provide the solution to the large problem. This is a recursion. If you've ever taken mathematics courses, you've seen the following. You've seen the following sequence, the Fibonacci numbers, which says that to find the nth Fibonacci number, I just take the n minus 1th Fibonacci number and add to it the n minus 2nd Fibonacci number. This is a recursive process, because if you asked me what is the nth Fibonacci number, I have to call the same process, the same Fibonacci process, on the n minus 1st value as well as the n minus 2nd value on two smaller subproblems. And then I recombine the solutions via addition to give you the solution to the nth problem, to the larger problem. This is also recursion. So this is the idea of recursive processes. I'm sure you've heard of these before. Now, the divide and conquer paradigm involves 3 steps at each level of the recursion. What are these 3 steps? Let's see. So divide the problem into a number of subproblems that are smaller instances of the same problem. So that's exactly what we did here, right? We divided our sorting problem into 2 subproblems that are smaller instances of the original problem. Step 2, conquer the subproblems by solving them recursively. If the subproblem sizes are small enough, just solve the subproblems in a straightforward manner. So here are our 2 subproblems. Now, we just assumed, or I just assumed, that we're a computer and we can sort lists of size 3. If we couldn't, we'd have to recursively split this into 2 subarrays. So we'd have maybe -2 and -2, -7, 8, like so. And now our job is to sort each of these 2, and these would get split as well. This would become -1 and 3 and 4, and we need to sort these as well. So this is recursively calling the same problem, the same procedure on smaller subproblems. And now -2, we obviously know how to sort. There's nothing to sort. It's a list with a single element. This is done. This is done. This is done. Okay, can we sort 3 and 4? Maybe you say, no, we can't. Okay, well, split this. We'll get 3 and 4, right? These are single element lists. This is done. This is done. Now we have to recombine them. How do we recombine them? Through the merging procedure that we went through before. And when we merge them together, of course, we get 3 and 4 back. And once we get that back, this is done. So -1 is done, 3 and 4 is done. We need to recombine them. How do we recombine them? Through the merging procedure we went through before. And when we merge them, of course, we get -1, 3, and 4. And this whole thing is now done. So this is the recursive process. This is the second step here. We conquer the subproblems by solving them recursively until we reach subproblems that are small enough to which we can just say, okay, we know the solution to this, obviously. Okay. And here is the recombination step. Combine the solutions to the subproblems into the solution for the original problem. So in the case of the sorting procedure, the combined step was merging. In the case of the Fibonacci sequence, the combined step was adding them together, adding the results of the 2 subproblems together. All right. Now, here is the merge sort algorithm. Let's give it a look. This is one of the most important sort algorithms there is. It is, excuse me, I needed some water. It is basic in nature. Um, there are more interesting algorithms. I personally find something like radix sort to be more interesting just because it's more mathematical in nature. But merge sort is really easy to understand, and it's quite powerful. So let's go through it. Merge sort algorithm closely follows the divide and conquer paradigm. Intuitively, it operates as follows. So here's our divide step. Divide the n element sequence to be sorted into two subsequences of n over 2 elements each. So you take a list of n things, you divide it into two lists whose size is half of the original. That's exactly what we did up here, right? We had a list, we divided it into two lists, each of which had a size half of the original list. Okay. What is the conquer step? Sort the two subsequences recursively using merge sort. So what is he saying? He's saying, okay, now do the same splitting that you just did on these two sublists. Well, it's exactly what we did here. This one got split into -2 and well, I should not have put -2 here. -2 and -7 and 8. And the left one got split into -1 and 3 and 4. Okay, what is the next step? We'll merge this. So sort recursively, right? Recursively. We are not done yet. -1, we're done. There's nothing to do there. It's list of size 1. It's obviously sorted. But this 3 and 4, we're not done yet. So since this is a recursive algorithm, we apply the same procedure on this small list now. It splits into 3 and 4. Each of these is size 1, so they're done. There's nothing to sort. They just have a single element. So now this conquer step is finished for these two sublists, 3 and 4. So we go to the step combine. Combine says merge the two sorted subsequences to produce the sorted answer. So the combine step is this merge process. Well, when we merge 3 and 4, we get this list, 3, 4. So now this merge process is done. This combine process is done for this list. So what does that tell me? Essentially, the splitting, the merge sort is now finished for 3 and 4, and it's finished for -1 because there was nothing to do there. So now we're at the combine step for these two guys. So we combine them using this merging process, and we get -1, 3, and 4. So now this left sublist is done. Now to the right sublist. -2, there's nothing to do. That process is finished. -7 and 8, however, we still have to merge sort. So this gets split. -7 and 8 gets split into -7 and 8. Now each of these guys is size 1, so they're finished. There's nothing to sort, so we just have to combine these guys, and we combine them through merging, and we get -7 and 8. So now this list is just finished its combine process. So now we have to combine the -2 and the -7 and 8. We combine them, and we get -2, -7 and 8. So now this right sublist is done with its combine process. So now we have to combine these two merge sorted sublists. We combine them through our merging, and we produce the final result. So now this final large list is finished with its combine process. Our algorithm is done. Okay. So the recursion bottoms out when the sequence to be sorted has length 1, just like we said here. When the sequence has length 1, merge sort is done. In which case, there's no work to be done since every sequence of length 1 is already in sorted order. So that makes sense. If your sequence has just a single element, there's nothing to do there. So the key operation of merge sort algorithm is the merging of the two sequences. in the combine step. So that's this merging process we just talked about. That's the key, right? Because when I get these two sorted subsequences, I have to put them together. And how do you go about doing that? That's our merging process. We merge by calling an auxiliary procedure called merge. It takes 4 parameters. Capital A is an array, and P, Q, and R are indices into the array such that P is less than or equal to Q is less than R. The procedure assumes that the subarrays A starting from P going to Q and A starting from Q plus 1 to R are in sorted order. It merges them to form a single sorted subarray that replaces the current subarray A from P to R. So what did that just say? That just said the following. So the way I presented this to you is I said, the way the picture presents this, you may think that there are two separate lists, the left sublist and the right sublist, and our goal is to merge them. Certainly in some languages, it's just simpler to implement it this way. Just these two are separate lists, and our job is to put them together. Now, other languages, such as maybe C++, such as maybe Java, etc. In Python, certainly that would be the case. But in something like C++, it might be simpler to say this. It might be simpler to say, I have this list, let's say -3, 4, 5, and -7, -6, -1. Now you notice that everything here is sorted. Everything here is sorted. So the splitting of the large list into the two sorted sublists is done implicitly. We haven't actually created two new sublists. It is the same list. It's just we're saying the list from this index P to this index Q constitutes the left sorted sublist, and the index from index Q plus 1 to index R. Let me see, was it R? Indices into there, such that we get into R constitute the left one, or the right one, the right subarray. Okay. Now, the procedure assumes that the subarrays from Q plus 1 to R are in sorted order. Yeah. It merges them to form a single sorted subarray that replaces the current subarray from P to R. So it merges these guys into a new subarray, that replaces this whole thing. Okay, so this whole thing gets replaced by a new array. All right. So our merge procedure takes time, theta n, where n is r minus p plus 1. Why is that? Why theta n? Well, we said before, right? When I'm going through the merge procedure, at each step, one element from the total number of elements here gets tossed out. So one element per one element each step. How many elements do I have? N. So how many steps am I going to do? N. Well, now looking at this example, how many elements do I have here? I of course have. So this index is P, this index is R, and so I have R minus P plus 1 elements in total. Okay, so the running time is, again, theta of n, but n, of course, in this case is R minus P plus 1. So that's where this number is coming from. It's a linear time algorithm. We wish to merge the two piles into a single sorted output pile, which is to be face down on the table. Let's see. Okay. Let's look at the pseudocode. So here's our algorithm. We're going to look at the pseudocode first. and there's a nice picture that describes the process. Let's look at the pseudocode. So the following pseudocode implements the above idea, but with an additional twist that avoids having to check whether either pile is empty in each basic step. We place on the bottom of each pile a sentinel card, which contains a special value that we use to simplify our code. Okay, what card? What is he talking about? Well, we skipped a bit. Let's go back and read that part. Suppose we have two piles of cards face up on the table. Each pile is sorted with the smallest card on top. We wish to merge the two piles into a single sorted output pile. So this is the merging procedure we just talked about. Our basic step consists of choosing the smaller of the two cards on top, removing it from its pile, which exposes a new top card, and placing this card face down onto the output pile. We repeat this step until one input pile is empty, at which time we just take the remaining input pile and place it face down onto the output pile. Okay, computationally, each basic step takes constant time. Okay, since we perform at most n steps, merging steps takes O(n) time. So they're saying exactly this. They're saying, so here's you can think of this subarray as our left pile of cards. This is our right pile of cards. At each step, you take the smaller card and put it face down. Take the smaller card, put it face down on top. Take the smaller card, put it face down on top. So you can see when this procedure is done, you have a face down cards. You have a pile of them face down, where the topmost card is, of course, the largest one. It's this 5. Okay, so if you were so in that sense, this becomes completely sorted. So this is our merge procedure that we just talked about. Now, so let's go. So let's see, what is the sentinel card they're talking about? The pseudocode has a twist with an additional twist that avoids having to check whether either pile is empty. Let's go through this. We place on the bottom of each pile a sentinel card, which contains a value that we use to simplify our code. Okay, so here's the problem. Here's what they're saying. Before we look through a pseudocode, let me quickly explain what they're saying. Suppose we had this. Suppose we have -7, -3, -2. This is our left subproblem that's been solved, sorted. Here's the right one. 1, 2, 3. We want to merge these. We'll always start. -7 goes here. -3 goes here. -2 goes here. Right? At each step, we're comparing, right? 1 compares to -7. That was smaller, came here. 1 compares to -3. That was smaller, comes down. 1 compares to -2. That was smaller, comes down. So what do I do next? Next, I would have to say, well, this list is empty. There's nothing to compare to anymore. So just take the remainder of this list and put it here. So in my code, I would have to have that extra logic that would say, hey, is this list empty yet? If it's empty, just put this guy over here. I would have to have this if statement. Now, what CLRS is doing in its pseudocode is it's putting this special value. I mean, I don't know if this is exactly what they're doing. We'll see soon enough. But I'm assuming this is what they're doing. -7, -3, -2. Now imagine having this. Let's see here. Having positive infinity here. This symbol. This is not a number. You just imagine having this positive infinity here. So, and our number is 1, 2, 3, for example. Okay. Now, if we wanted to, let's say we put positive infinity here too. Now, if we wanted to do merging here, again, 1 compares to -7, that comes down, to -3, that comes down, -2, that comes down. Now 1 compares to positive infinity. Obviously, 1 is smaller, that comes down. 2 compared to positive infinity, 2, that comes down. 3 compared to that comes down. Positive infinity to positive infinity, at that point, we're done. So somehow I wonder how they do this positive infinity to positive infinity check, if that's there at all. But the point is that even though this list was officially over, I didn't have to check whether it was over or not. The comparison naturally continued. It's just that everything in the right list is obviously smaller than positive infinity. So by the nature of merging, these numbers will just come down into this list. I'm assuming this is what they're talking about. We'll see right now. Okay, so let's go through this pseudocode. Let me erase this stuff. Let's go here. So if you can tell, I'm learning this stuff with you. This is not, maybe at some point, actually, I'll start rehearsing these streams before I stream them. I'm learning this with you, along with you. So, you know, this is the process in its most natural state, I suppose. All right. So here's merging. We have some array. And we're going to do an example. We're going to make an array, which will be -4, 6, -2, 7, 3. This is our A. The algorithm starts, N1 is Q minus P plus R. Okay, so what is P, what is Q, what is R? In detail, the merge procedure works as follows. Line 1 computes the length of the subarray P through Q, and line 2 computes the length of the subarray from Q plus 1 to R. Okay, so remember that these are the two splits that they're going to make. These are the two splits that they're going to make. So let these be the two new arrays, from 1 to this number and from this number to here. And then they go from so they're going to call the same. This is the merging procedure, by the way. This is not merge sort yet. This is the merging process. Okay, so what is this saying? This saying is if you want to merge two arrays that have to be sorted. Okay, so all right, let me erase this. This is not a very good example. Let's construct the example again. So here's our A. A consists of -1, -2, -3, -4, -3, let's say, or maybe not even that. Let's do this. So this consists of 1, 2, 3, -2, -1, and 7. Now this is A. We need to merge them. Well, we need to provide the indices, right? So the in P, Q, R. N1, so look, the left sublist is going to be from the first element to this N1 plus 1th element. Now, the thing to know about CLRS is that it doesn't start its count from 0. It starts its indexing from 1. Okay, so that's this element here. So we want to say P is, so this is P, this is Q, okay? And then we have R. So N1 is Q minus P plus 1. Q minus P plus 1. Let's see, Q, P. Q minus P plus 1 is, of course, going to be 3 in this case. So that's 0. So like 1, 2, 3. That's 3 minus 1 is 2. 2 plus 1 is 3. That gives us 3 elements. So Q minus P plus 1, that's N1, which is 3 in this case. So N1 is 3. Now, R minus Q should be the number of elements in the second subarray, R minus Q. Well, if this is R here, then how many elements are in R minus Q? Well, this is 1, 2, 3. So 3, 4, 5, 6. 6 minus 3 is 3. 3 plus 1 is 4. There are 4 elements. So N2 is R minus Q plus 1, which is in this case 4. Oh, r minus q, not r minus q plus 1, r minus q. Okay, now r minus q plus 1. So if I set n2 equal to r minus q, look what the issue is. So q, starting the indexing from 1, this is 1, 2, 3. R minus q then, so 3, 4, 5, 6. R minus q is 3, right? So if you're pedantic enough, if you look over here, if you look a bit in the definition of merge sort, you'll see that q is strictly less than r. Q is strictly less than r. So if r, this higher bound, is one larger than the actual than the largest element in the list, then r minus q is equal to 4. Okay? All right. So what happens next? So L from 1 to n plus 1, n minus 1 plus 1, that's our left. And then from 1 to n2 plus 1 is the right part. So here is our right, here's our right part. Here's our left part. Then we start going. So for each step through our left subarray, we set, so Li equals AP plus I minus 1. So what does that mean? So we have this left subarray. We're saying each element in the left subarray is going to equal to the A starting from starting position. Here's our A. We're going to go through starting from P. We're going to keep going. See this I, this index. We're going to keep going through there. Minus 1. Okay. So why minus 1? Because I starts from 1, right? I want to capture that pth position. So when I equals 1, I minus 1 will give me 0, so I'll get A subscript P, the pth element in A, which I want. So in other words, all these elements get put in an array called L. This becomes L. And then we go from 1 to n2, and from q to j, all the elements go into this right sublist. So these guys go into R. That's the lines 6 and 7. And now look what he does. Exactly as we suspected, he actually has another element, n plus, so this extra one element. That's why he allocated an extra space here in these two arrays for the infinities. So aside from 1, 2, and 3, this L will have a positive infinity, and R will have a positive infinity as well. Like so. Now he sets up two indices, I and j starting from 1. And remember, the indexing in CLRS is starting from 1. If you encode, these would be zeros. So now he's saying we're going to go from P to R. P to R. P to R is, of course, this whole thing. We're going to go from here to here. And what are we doing? We're going to check each. So this I is here right now, and j is here right now. We're going to compare those two elements. If the left array's element is smaller than the right array's element, then in A, inside A, in that kth position, k, remember, is currently at P. K is this right here at P. So in this position, we're going to put the smaller one of these two. Okay. I don't know why I actually wrote the same numbers here. This is a mistake. I apologize. This is supposed to be -2, -1, 7. So which one of them is smaller? -2, right? So right here, we're going to put a -2. So this is going to go away. This becomes a -2. K moves over. K is now the second position. And since we put this -2 there, remember that -2 gets crossed out, and j is now at -1. So -1 gets compared to 1, right? So see, the I, this arrow that was pointing here, this thing right here, moved over. And now the comparison happens again. Which one is smaller, the left one or the right one? Well, the right one. So the right one comes here and replaces the 2. This is a -1. K moves over here. J moves over. Same process happens again. Which one is smaller? Well, now this 1 is smaller. So the 1 gets crossed out. The 3 gets replaced with a 1. And I moves over. So which one is smaller? The 2 is smaller. 2 gets crossed out. This 1, the 1 stays. I'm sorry. The 1 stays. This -2 becomes a. Did we copy these? This is 1, 2, and 3. Yeah. So this next number becomes this 3. The next number becomes the 7, and so on. So now we're going to reach through state. When we go through 2 and 3, we're going to reach a state where I reaches the infinity. When I reaches the infinity, we have to compare the infinity to 7, right? So now when we compare infinity to 7, obviously the left element, the infinity, is larger than the right element. So we hit this else case. The left element is larger than the right element. And so the right element goes in A. This right element, the 7, goes in A. 7. This guy moves over. Now they're both at infinity, right? They're both at infinity. And when they're both at infinity, since we're going up to R, here, at that point, we're done. There's nothing to insert anymore. We are at infinity. And this is why I said R should be one larger than what your element is. Why should than what the size of the array is? Why should it be one larger? Because you're accommodating for these infinities. You've added an extra element. When you reach this R, when you're merging these values, when your loop reaches R, you stop. Okay. So this is the merging process as defined here. Now, I definitely encourage you to try edge cases. It is extremely important for your development of your intuition to try edge cases. What are edge cases? Suppose your A looks like this: -3, and then you have 1, 2, 3, 4, 5. Suppose, and this is your P. It is your Q as well, and your R is here. Remember that from P to Q inclusive is your left subarray. So essentially you're saying that you want your left subarray to just be the singleton. And then everything, so from R minus Q, you want to be your right subarray. So your right subarray is just everything over here, right? So it's 1, 2, 3, 4, 5, and you want to merge these. In fact, I'd go even further. I'd say, what happens? Can I possibly make it so that can I specify the algorithm somehow so that my left or right subarrays are empty? Is it possible according to the definition? Let's see. P, Q, and R are indices into the array such that P is less than or equal to Q, less than R. So they're indices into the array. Okay, so it almost sounds as though if your array is not empty, What if your array has a single element? It's -3. Well, then this will be an index to the array. It'll be P. It'll be Q. So that's your L. Your left subarray is -3. Your right one points here, right? Your R. So R minus Q, the rest, in other words, should be the right subarray, but there is no rest. So the right essentially is empty. Now, what would happen in that case? Well, according to the algorithm, you'd put an infinity here, you'd put an infinity here. So -3 would get compared to the infinity, -3 would get put into place, then infinity to infinity, you'd be done. But again, I suggest going through the pseudocode and making sure that you understand edge cases, how the pseudocode does edge cases. This fact that R seems to be one extra step, one more than the size of the array to accommodate for the infinities throws people off. But this is a really nice, clever method of avoiding that extra check, of doing that extra check whether if one of the lists is finished. So definitely go through it. In fact, I also suggest coding it up. Use Python, use Ruby, use C++, whatever you're comfortable with. Python is very nice to code up algorithms because you get to the crux of the math and you don't get bogged down in allocating memory, etc. So go through it, give it a shot. Now, pictorially, this is you can see pictorially what's going on here. Here's a list. So here are our splits. So he splits into 2, 4, 5 and 1, 2, 3. Okay. He puts so how do you merge these two lists? In other words, how do you merge these guys? Well, you put the infinities and you go through the merging procedure as we described. All right. Let's see. Let's give this part a read. The merge works as follows. Line 1 computes the length n1 of the left subarray. Line 2 computes the length of the right subarray. We create arrays left and right of lengths 1 more, respectively, in line 3. You can see that here. The extra position in each array will hold the sentinel. Sentinel are our infinities. The for loop of lines 4 and 5 copies the subarray A from P to Q, that's this left subarray, into the left one, right? We created this left subarray, but it's assumed to be empty. There's nothing there. So we copy that part over. Then we copy the right one into R. Lines 8 through 9 put the sentinel into that last position. Lines 10 through 17, illustrated in figure 2.3, perform the R minus P plus 1. R minus P plus 1, remember that's the number of steps for the merging. So they perform these merging steps. So the merging is depicted here. Well, let's see how it's depicted exactly. So we have a list. This list is to be split 2, 4. Yeah, okay. So 2, 4, 5, 7. So if this is our original list right here, then it gets split into this left one. See, 2, 4, 5, 7 is our left one. 1, 2, 3, 6 is our right one. The sentinels get put. And now the merging process begins. So we compare, okay, yeah, I see it. So we compare the 1 to 2. Which one is smaller? 1, right? So that gets put in this position. K moves over here. Now we're comparing the 2 to this 2. See, the 1 is blacked out. We remember what merging does. Each time through the iteration, it tosses out one of the elements from either of these arrays. Since we put the 1 here, This 1 is now crossed out. There it is. Now comparing this 2 to 2. So whenever they're the same, I suppose just by the way the code is written, he takes the element from the left array, as you can see here. So he takes the element from the left array, puts it here. This one's crossed out. The pointer moves over to 4. 4 to 2. 2 is smaller. 2 comes there. Pointer moves over. 4 to 3. Okay? So 3 would be put here, etc. And this process continues until we hit infinity to infinity, and at that point, the loop stops. All right, so let's give this a read. At the start of each iteration of the for loop, the subarray contains k minus p smallest elements of the left array and the right array in sorted order. Okay, so since at each iteration we can assume. So remember, we start with p, right? The leftmost index in A is p. Let's look at this image C here. We're now at index k. The first one is p. Where how many elements are here? K minus p, right? So the subarray from p to k minus 1, so that's p, and that is k minus 1, can be assumed to be in sorted order. It contains the smallest elements of this left subarray and the right subarray in sorted order. How did we put the 1 and 2 and 2 here? Well, from the left and the right arrays at each step, we put the smallest numbers in here. So we can now assume that 1, 2, and 2 are in their correct positions. They're the smallest values from the left and the right arrays, and they're sorted because that's how merging works. It takes into account how big the numbers are. So we can assume that the elements p plus 1, and k minus 1 here, they are sorted. And that's exactly what this line says. And that's our invariant through the loop. So we must show that this loop invariant holds prior to the first iteration of the for loop of lines 12 to 17, that each iteration of the loop maintains this invariant, and that the invariant provides a useful property to show correctness. Okay, so we need to show that that procedure is correct when we initialize, when we go from iteration to iteration, and that at the termination of the loop, of the procedure, that property still holds, that these numbers are the smallest numbers from the left and right subarrays in sorted order. Let's think about this. When we start maintain, so let's see, where's initialization here. Prior to the first iteration of the loop, we have k equals p. So as we can see here, k points to the very first element in the array. So that the subarray p to k minus 1 is empty. This empty subarray contains 0 smallest elements of L and R. And since I and j are 1, see these two indices here are 1 because we haven't started yet. Since they are 1, both L and R are both Li and Rj are the smallest elements of their arrays that have not been copied back into A. Okay, so this initialization is essentially saying that, remember, the algorithm says starting from P to K minus 1, the array holds the smallest elements from these two guys. Now, if P equals K, then P to K minus 1, from P to K minus 1, is an empty list. It has nothing. And since if it has nothing, just by convention, we just say, you know, since it holds nothing, it holds the smallest values. And that's the initialization. Now for maintenance, to see that each iteration maintains the loop invariant, let us first suppose that the left element we're looking at is smaller than the right one. Then the left element is the smallest element not yet copied back into our list. Because our list from P to K minus 1 contains K minus P smallest elements, After Li gets copied into our original list, the subarray from A to Pk will contain the smallest elements. Okay, so what is he saying here? He's saying, suppose we're at this step. Now, and we know that these first four elements are the smallest elements from the left and right arrays, and they're in sorted order. Okay, now we're about to do the next step. What does the next step say? The next step says compare 4 and 6. Whichever number is smaller, in this case the 4, we're about to put in this 13th position in our original array. Because the smallest elements from all L and R are now here, we know that this 4 is larger than the previous values. Then it's larger than the 3, then the 2, then the 2, then the 1. And so when we put the 4 over in this picture F, when we put the 4 here, this sublist of these 5 elements is again sorted, because again 4 is larger than everything before it. Okay, 4 is larger than everything before it, and again these first 5 values are the smallest values from the left and the right subarrays. So this property holds from iteration to iteration. Okay, so here is the merge sort, the merging process, merge sort process. Merge sort process is very simple once you've understood the merge. So again, I strongly recommend you go through this merge pseudocode, try edge cases, and then try writing the code yourself. And then go through this picture again, and once you've understood this initialization and maintenance and termination, then look at merge sort pseudocode here. Merge sort is quite simple once you've understood merging. All right. So again, if you have any questions, hop on the Discord, ask away. I think I understand this process, but me, myself, what I'm going to do after I log off, I'm going to go through the pseudocode again, and I'm going to go through edge cases, just like what I told you to do just now. I'm going to do it myself. So have a great evening, and I'll see you guys tomorrow.